Do you see her?
No.
Then she's not here. That's how that works. That's how that works, Zoe.
People can still see it.
If you walk in and you don't see them, they're not here.
Why so unfazed?
What?
Why so unfazed?
I still have faith that she's going to be here too, but just not as much as before.
I know, why so unfazed?
Okay, eat your thing if you're going to eat it in class because you got to be done before class starts.
I know.
You got a minute and 2 seconds.
This is the best thing.
The best?
Oh,
Best list? Okay.
I
I
knew.
mean, you got 3 black ones. You can wear one each day of the week almost. Okay. That's a good plan. That's a good plan.
Okay, so number 2 is him.
Hello, Jaslyn.
Really?
Morning. You were always such a
Yeah, that was exactly it. Only that I was in the front. I was in the front and I took it. Just like. Oh my god.
Good morning, ladies and gentlemen. How are we doing today? Good. Put it away now. You gotta finish it later. Okay. Put away your food. Put away your phones, ladies and gentlemen. Your headphones out of sight, out of mind. Let's go. We're getting into starting class. Open up your computers and go to joinpd.com, ladies and gentlemen. Joinpd.com. All right. All righty. Alexa, no. Kiana, no. Yes, Let's see.
You want to be that picky?
No.
He's to the point where he like.
You want to be that picky, computer? A computer has to be that picky.
Well, Zoe, if you charge it at night, you wouldn't have this problem.
I knew.
I know that, but what's going on?
I take too long talking.
Well, stop talking to people. They really don't want to talk to you anyway. Come on, move it. All right. All right.
What's all cold?
Right there, Zoe. GLJJEZ. That's your code, ladies and gentlemen, for your Pear Deck. JoinPD.com. GLJJEZ. That's your code so that we can get going today, ladies and gentlemen.
Yeah, really.
So,
Yeah, like people can be exothermic. Yeah, really.
what's that?
People, yeah, green. Some, I mean, joyfully, some.
Exothermic zebras. Can
Yeah,
zebras be exothermic?
Yeah, I sure can.
What does exothermic mean? You know it. This is the term we've taught you in this class.
I know that.
Exothermic.
It comes out.
What comes out?
Over the heat comes out.
Heat is leaving. Heat is exiting. Very good. Very good. See that? Even the Pear Deck is teaching you today.
Oh yeah.
All right.
What do you use of a peel deck?
Okay.
What if we use of a peel deck?
No, wait, put that away. Come on, we're going to do a bunch of stuff today.
JoinPD.com.
All right.
Get there.
4, 5, 6, 7.
You just type it in your up there. Right there.
Okay, just a reminder, ladies and gentlemen, on Friday, you will be taking a quiz. Your quiz will cover the energy portion that we have done the last 2 days. So that is what your quiz will be on. What we are going to start today is going to be the basis for the lab that we will do tomorrow, okay, and finish up into next week. So We're going to start talking about energy today, but the stuff that we're doing today where we're actually calculating energies, that will not be on your quiz this week, Friday. Knowing the types of energies, kinetic and potential, knowing the different forms of energy like was on the worksheet, that is what is going to be on your quiz tomorrow, just so you know. So, ladies and gentlemen, let's take a look at this and let's get moving. Okay? So, all right, for today, ladies and gentlemen, we're going to be able to start calculating how much energy is released by food. We'll get into that in a little bit, okay? You got your new periodic table. Please remember you can use it on the quiz on Friday. You can use your solubility chart on the quiz on Friday. So any notes you want to take and put on there. Anything about energy, kinetic potential, about electromagnetic, about heat thermal energy, about nuclear energy, any notes you want to put on there, you are welcome to, and then you can use on Friday, ladies and gentlemen, okay? We're going to talk about the worksheet that I gave you. I'll actually give you a few minutes to work on it today after we do this pair deck, and then we will get going into our measuring energy stuff, okay? So, and then, ladies and gentlemen, I do have another worksheet for you today on calculating energy. We'll just get started on it. You've got until the end of the week to get that one done. So here we go, ladies and gentlemen. Choose the form of mechanical energy for the following example. A bird sitting on a power line. Does that have kinetic energy, elastic potential energy, both kinetic and potential energy, gravitational potential energy, chemical potential energy? Which one do you think this is the best example of, ladies and gentlemen? Drag your cursor and put it on the one that you want to choose.
Mr. Brown, can I ask a chemistry question?
Sure.
So so you know how that when there's that experiment when they put a pickle on a thing and it lights up, right?
Yeah.
How does it light up?
Because the electrolytic solution in there, which is pickling brine, which is salt water, it glows when you put an electric charge to it.
It's just a random thought.
Good. Now, randomly answer this question.
I already did.
Okay, good. Let's see what you got. Okay, first of all, it cannot have kinetic energy. Why?
It's not moving.
Not moving. Now, again, you could say the bird is breathing, things like that, but probably not the best example for this one. Okay? So I would not have expected you to put kinetic energy on there, which also eliminates both kinetic and potential because it's just sitting on the power line. Elastic potential, I don't know how you could get elastic potential out of this because the bird isn't being stretched. There is nothing that is being deformed, things like that. Now, I would have accepted gravitational potential. That was the energy I was going for. That's why we said it was sitting on a power line. Power lines are above the ground, ladies and gentlemen, meaning the bird can fall. I would have also accepted chemical potential energy because you could say the bird eats food or the bird could be used as food. A little more of a stretch here, but that one would have been acceptable. So of the two, the one I was looking for was gravitational potential. Could possibly do chemical potential. All right. All right. So now our next question, ladies and gentlemen. The one I was looking for was, again, gravitational potential. The best example is what I'm looking for. A wheat field. Would that be an example of kinetic energy, elastic potential, both kinetic and potential, gravitational potential, or chemical potential? So which one do we think that would be representing, ladies and gentlemen? And this one's a little bit more obvious, I believe.
My baby on.
Okay, again, to be kinetic energy, you have to be what? Moving. If they would have said something like wind blowing through a wheat field, where it would be moving back and forth, I could understand how you would say kinetic. But a wheat field, wheat just standing out in the field, not kinetic energy, ladies and gentlemen. Not kinetic energy. The one that we were going for, ladies and gentlemen, was chemical potential. Why? Because it's food. It is food for animals or it is food for people, ladies and gentlemen. It will provide calories. I don't know who stole my other cord because there were two cords here. Who's got the cords, ladies and gentlemen? Oh,
I just
sorry.
used it.
Sorry, I didn't. Good question. All right. So here we go. The spring on a garage door that helps in lifting the door, ladies and gentlemen. The spring on a garage door that helps to lift the door when the door is opened or closed.
There's 2 answers for it. 3 answers for it.
Nope, there's only one answer for this. There's only one right answer for this. It doesn't say that the door is open or closed. It says it can be helped to open the door, to lift the door. All right, good. Again, ladies and gentlemen, because the spring is not moving, it cannot be kinetic. But helping to lift the door, the spring uses its elastic potential energy. It deforms, okay? It will either stretch out when the door is closed so that when you lift it, it helps close, it helps open it, or there are springs that literally turn, like the ID badge I have here where it spins around, creates tension so that when you need help lifting the door, it can do so. All right. A train speeding across a bridge. A train speeding across a bridge. Now, it is important where the train is at, what the train is actually doing, ladies and gentlemen, because it helps you to get the correct answer here, and there is only one correct answer for this one, ladies and gentlemen. All right, let's see if we all got it. Well, we did get everybody putting kinetic, which is good. But why is it both kinetic and potential? And what does being on a bridge mean? Being on a bridge means that it could fall off. It could fall down. If you are going over something on a bridge, you are above the lowest level. Okay? Did anybody see the news the other day where the truck driver's truck actually went off of a bridge? Really? Your dad is a female because that's who they got out of the truck. Did you actually see it, or are you just being a smartass? Okay, good. Anyway, ladies and gentlemen, an 18-wheeler went off of a bridge, and literally the tractor trailer was hanging just by the trailer behind it. And they had to bring in a crane, and they sent a guy down on a crane to get the person out of the truck so that they didn't fall into, I think it was the Ohio River. Okay? Good example of potential energy sitting there, ladies and gentlemen. And I would assume that driver was trying not to use any kinetic energy because thinking that if they moved too much, they could have fallen out of the truck. So because you're on a bridge, you would have both, ladies and gentlemen. Okay? So again, when you give me an example, yesterday I asked people in my 5th hour for an example of something with both kinetic and potential, and they said an airplane. Does an airplane have both kinetic and potential energy?
Yes.
No. Not unless it's doing what?
Moving.
Not unless it's flying. Even moving. You could say, well, the plane is moving across the ground, so it would not have which? Potential. So remember, you got to be specific. Then they tried to tell me, well, a baseball would have kinetic and potential. It would if it's doing what? In the air, being thrown, hit, somewhere in the air. You need to make sure you are specific enough to where I can't look at your example and say, no, that's just sitting there. That wouldn't count. Okay? So please be specific. All right. All right. Good, ladies and gentlemen. That was our ones for today. So here's what I've got for you, ladies and gentlemen. We are going to give you about 15 minutes to get the worksheet that I gave you yesterday done. Okay? So the worksheet that I gave you yesterday was the one on energy it was the energy worksheet. This is what it looked like, ladies and gentlemen. We're going to give you about 15 minutes here to get it done and get it turned into me today, ladies and gentlemen. Go to work on it. If you have any questions, I will be more than happy to answer them, to come over and help.
Mr. Brand,
What?
what kind of energy was it when back in the day when they would do water?
Water wheels would turn mechanical. Well, you use gravitational potential energy because the water would come out high, and it would cause the wheel to spin, turning it into mechanical energy. And then they would use that mechanical energy for other things. Okay? No, energy works. That's when this is space. I'm going to show right at the you come across something on that worksheet that you don't understand or you don't remember, it would be a good idea to put it on your periodic table because that's the stuff that's going to be on your quiz on Friday, ladies and gentlemen. Yes. Remember, anytime someone is moving or something is moving, it has to have kinetic energy. Potential, the most common kind is gravitational, which means it has to be above the ground. Okay? So,
Oh.
right. So potential energy depends on two things. It depends on how high the object is above the ground, and it depends on how massive it is. They will fall at the same rate, and that is true. Okay, so again, if you have a heavy object and a light object, and you drop them and they fall at the same rate, now they have the same speed. But remember, when they begin, an empty box and a full box up there, which one will have more potential energy? Why? Now, when they're falling, that potential energy turns into. So now, which one has more kinetic energy? Still the heavier one, because they're going to fall at the same speed. But now you look at the water bottles in the back, the one with the most potential energy, the coolest one, right? Because it has more water. Okay? So all those things are kind of interrelated. We've got a few minutes yet to work on the action minutes. The energy worksheet, then we're going to talk about the capital. We got about 5 minutes left, ladies and gentlemen. So you still have time, but if you have questions or if there's something on there that you need help with, you only got me for about another 5 minutes, and we're moving on, ladies and gentlemen. The homework isn't due till the end of the day today, but this is the last 5 minutes you'll have in class to work on. Okay, well, let's look at it. which one can't be? Okay, so we can eliminate those. We know the definition, but it doesn't work. That's not what is the object? This is exactly. No, 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 no. Oh, wait. Oh, okay. No, no, no. You were reading the definition. So, force applied to an object that makes it move a distance. Yes. Or, so what are your definitions? This one, energy transmitted away, radio and TV. What was that up there? So, energy, they easily charge the electron. A little bit of electron is enough. Well, an object that is moving down the hill, you add up its kinetic, you add up its potential. Okay, couple things I want to let you know, ladies and gentlemen, so if you'd give me your attention. At the end of the trimester, when I calculate your grades, the computer says that if you don't get a 90.0%, you don't get an A. Okay? If you don't get an 80.0%, you don't get a B. So somebody who gets like an 89.5 always comes up to me and goes, well, Mr. Brand, can you round that up? Well, the computer doesn't. But I can. I can choose to round that up. So what makes my decision a lot easier, ladies and gentlemen, is when I look at your grades over the trimester. If I look and see a ton of blank things that you didn't do, I will not round your grade up because you had the opportunity to turn things in that would have done that for you. But if I look back and all of your stuff is turned in, I'm going to give you the benefit of the doubt. I will round your grade up for you. I will take that 89.5 and make it into a 90. I'll take the B minus and make it into a B, or the C minus, and I will make adjustments for you. I always look for grades that are close. And then I decide, okay, going back and looking at your grades, did you basically do enough to where I can give you that extra? So again, I don't grade your homework, ladies and gentlemen. But it is something that I look at the end when I'm deciding, okay, should I give this person the benefit of the doubt? Did they do what they were supposed to do in the class? So consider that. And the homework is not hard. And I'm not going to base it on if it's right or wrong. So I don't go through it and go, oh, you got this one wrong, you got this one wrong, you got this one wrong, therefore you don't get 100% on it. If you complete the homework and turn it in, even if your answers may not be right, I'm going to give you credit for it. Okay? Now, it doesn't do you very much good to do the homework and get the answers wrong, because that's not what homework is for. It's practice. And that is why I put the answer keys out there for you right away. Now I'll have other people be like, oh, he puts the answer keys out there. I'm going to copy all the answers and put it into the homework. Go ahead. Go ahead. That's not going to help you when it comes time for the test or the quiz. And since homework doesn't affect your grade, you doing it that way, well, it may get it done for you, probably is not helping you. So again, ladies and gentlemen, this is an upper level class. I'm treating you like the juniors and the seniors that you are, giving you your options and explaining things to you. So you can do it however you want, ladies and gentlemen. Now, the one thing I don't like is when two people sit next to each other and the one has their homework done and the other one doesn't, and they just copy it. If you're going to do that, copy it off of my key. Don't copy it off of your friend. Okay? So keep that in mind, ladies and gentlemen. Okay. At the very basics, ladies and gentlemen, by the way, open up your EISN. Please get to slide number 14. That's where we're at right now. Why do we eat food? That is our only source of energy, ladies and gentlemen. You and I cannot get energy unless we eat and process food. And the body is set up to do that. The body is set up to take any calories you give it and process it into energy. But there are certain kind of calories that the body uses easier to make energy. Ethan, question, go.
This is
Just, let's go.
What
Go.
about caffeine?
What?
What about caffeine?
What about caffeine? It doesn't give you energy. It is a stimulant to make your nervous system work. I don't want to say the word better, but a stimulant will cause your body to be in a heightened state. Doesn't give you energy though. Okay? So caffeine does not give you energy because it doesn't have calories. Now you can do things to your body to make it be more stimulated or less stimulated. But again, the only way you get energy is from the foods that we eat. Okay? And again, depending on what kind of foods you eat, determine what kind of calories you get. Okay, so we will get into talking about the difference between a carbohydrate and a fat, and the difference between a fat and a protein, and the difference between those things and vitamins and minerals. Okay? But understand, fats, carbohydrates, proteins, all have calories. They're all sources of energy. Okay? Now, the body can process some of those easier than others, but again, we will get into talking about that. Now, the government requires that when you put a substance out, a food substance out, the FDA requires that you test it and you be able to tell people the number of calories in it and where those calories come from. So if you look on the label of a candy bar, it will tell you where its calories come from. It will tell you how many calories. It'll tell you how many servings. And it'll tell you exactly how much energy you are taking in. Now, yesterday we said kinetic energy was measured in what unit?
Joules?
Joules. Potential energy measured in joules. Food energy we measure in calories. And the reason for that is there is more actual energy in a Snickers bar than in a stick of dynamite. There is more energy in a Snickers bar than in a stick of dynamite. But you and I cannot take a Snickers bar and use it to blow something up. No more than you and I can eat a stick of dynamite. We couldn't process the energy from it. They're different kinds of chemical energy. But what it tells us, ladies and gentlemen, is the foods that we eat and the way our body processes them, we get a ton of energy out of them. Okay? Enough energy to blow things up is what we need in our body on a daily basis to keep it functioning properly. Okay? So again, if they come up with a new kind of candy bar, they have to test it and they have to put the calories on it. We're going to do a lab that simulates how the government tests food before they can sell it by figuring out how many calories are in it. So it is a process called calorimetry. Calorimetry is a process where they measure the energy in food so they know how much energy is there. So it is the science or act of measuring energy given off by foods when they burn. Okay? When they burn. Now, our body burns them in a different way. There's not a fire inside us from the Snickers bar you ate last night burning it up. But we are going to burn foods in the lab to see how much energy is in them. Okay? We're going to measure the heat transferred from the burning substance to the environment. So we're going to take that heat that is given off by the food as it burns. We're going to try to capture it. And we're going to try to figure out how much there is there. Okay? It's measured in the unit of energy. That is not right. Joules are for heat energy. Calorie is for heat energy. This is a little c calorie. And then there is a big C calorie. That is for measuring food energy, ladies and gentlemen. So I know this is weird, but there is a difference in unit here if you capitalize the C and if you don't. So these can be used to measure heat energy. How much heat comes off of a stove, how much heat comes off of a burning object, things like that. These calories are strictly for the foods that we eat. Strictly for the foods that we eat. Go ahead, what?
I was just saying, isn't there a calorie that starts with a K?
You're thinking of Kelvin.
Kelvin.
Kelvin starts with a K and Kelvin measures temperature. Okay? Now remember, calories, energy can affect temperature, but they're different units, just so we're clear. Okay? All right. A little c calorie measures heat energy. It's the amount of heat needed to raise 1 gram of water 1 degree Celsius. That's how we measure heat given off by something. We see how much water and how much temperature change will happen to that water. Okay? Now, you remember in the earlier unit when we talked about specific heat in the first part of this class?
Oh, yeah.
And specific heat was the ability of something to heat up easily or difficult. We talked about going to the beach and the sand heats up really quickly because it has a low specific heat.
Oh, yeah.
Water had a
Hi.
high specific heat. So it's actually difficult to heat up water. And that's why they use it for this measurement. Okay? Because it's difficult to heat up. Okay? It's used to measure the heat transfer, and the formula is this. A little c calorie is equal to the mass of water times the temperature change in water. So if we know how much water we're heating up and we know how much it heats up, we can figure out how many calories of energy were in that food. That is what we are going to be doing.
Need a calculator.
You're going to in a minute. But this is our formula. We'll be working with that in a second. But a food calorie is actually 1,000 times bigger than a little c calorie. So a food calorie measures the amount of energy in food specifically. A capital C calorie is for food and food alone. And it is 1 food calorie equals 1,000 little c calories. In other words, this calorie will raise 1 gram of water 1 degree Celsius. A food calorie is enough energy to raise 1 gram of water 1,000 degrees Celsius. or 1,000 grams of water, 1 degree Celsius. Yes.
So are these both like chemical energy? Like are they both chemical?
Energy is energy. It doesn't matter. You could compare them to potential. You could compare them to kinetic. You could compare them to electromagnetic. Energy is all measured in either calories, big C calories, or joules. Now, there are some other units, but these are the 3 most popular. But okay, we talked about that bouncing ball having kinetic and potential energy. Well, 1 food calorie would give that bouncing ball 4,200 joules of energy. That's a lot of energy. That is a lot of energy because you would have to have a pretty heavy object moving at a pretty good pace or sitting fairly high off a shelf to get it to have that much energy. Okay? But yes, they're all related. All related. But we only use this calorie to measure food. Okay? We could convert food calories into joules. We could do it, but instead we use this. Why? Because in joules, it would be a really large number. Think about a Snickers bar. Snickers bar has about 300 calories in it. 300. This is 4,200 joules per 1 calorie. So now we take that times 300. That's over 1 million joules of energy in 1 Snickers bar. Okay? A lot of energy in there. A lot of energy. Okay? Sorry, Snickers bar, 250 calories. I overestimated it, 300. If you had a bathtub full of 40 gallons of water, that would be 1,500 or 151,416 grams. These are numbers that I use for conversion. The energy in a Snickers bar, if we put it into little c calories, would heat that bath water by 2 degrees. And that's 151,416 grams of water. 1 Snickers bar would heat it 2 degrees. Okay? That's a lot of energy, ladies and gentlemen. A lot of energy. Okay? This, ladies and gentlemen, is a picture of how they test food. We don't have anything this complicated to use tomorrow. Well, literally what they would do is put the food inside this container here, and they would burn it with a small explosive device. It's called a bomb calorimeter. And then this is going to get what? Hot. And they measure it by this water all around it and how much the temperature goes up. Okay? Now, you and I cannot do this because we don't have these things, but we're going to find a different way of doing it. Okay? We're going to find a different way of doing it. Okay? So, here's where we are going to begin, though. How much energy is given off by a snack that can warm a case of water, 24 bottles at 500 grams each, from 19.5 degrees Celsius to 27.8 degrees Celsius? Okay? So the formula that we're going to use here, ladies and gentlemen, is we are going to use calories of energy is equal to the mass of water times the change in temp. Okay? The mass of water times the change in temp. Okay? Now I think, is this all done for you on your slide or no? Okay, then let's begin with this here. Whoops. Okay? So what are we looking for? Well, what are we trying to find? What's the question asking for?
How much energy?
How much energy? Okay? So in our formula up here, where is energy? And I'll point to the formula in just a second, ladies and gentlemen. In this formula right here, where's energy?
In the parentheses.
Okay, we're going to solve for energy. We're going to solve for this part right here. That's what we're looking for. Okay, so what are we looking for? We're looking for energy. So that's what you're going to type in here. What are we given? In the problem, what are we given? Look at the numbers and tell me what the numbers are.
24 bottles at 500 grams.
Okay, so what is this information telling us?
How much bottles we have?
Okay, but look at our formula.
How many?
Energy equals mass times change in temp. What is this actually giving us? The mass. This is giving us the mass, ladies and gentlemen. So the mass is equal to 24 times 500 grams, right? 24 bottles at 500 grams each. Somebody with a calculator, please take and multiply those two together and tell me what we get.
24 times 12,000.
We get 12,000 grams. Good. Okay. So then there is also this number here, 19.5 degrees Celsius, 27.8. Again, look at your formula down here. What is that giving us?
Total calories.
Nope. Yes. By the way, what does this triangle mean? Anybody remember?
Delta.
It is delta, and it means change. So instead of writing out the word change all the time, they will put a triangle in front of something. That triangle, delta T, this means change in temp. Okay, so that means change in temp. So we can figure out our change in temp here. Okay, it is 27.8 degrees Celsius minus 19.5 degrees Celsius. All right, so what does that give us, somebody? Come on, that's not hard math. Okay, 8 minus 5.
8.3.
8 minus 5. 3. 27 minus 19. 27 minus 19. So our change in temp is 8.3 degrees Celsius. Questions? Okay. Now hang on a second here, ladies and gentlemen. So for us to calculate the energy, ladies and gentlemen, we're going to put these numbers into this formula. So calories, oops, I almost made a mistake there, ladies and gentlemen. What kind of C is this? Lower. Don't accidentally write it as an uppercase. Calories equals the mass, 12,000 grams, times 8.3 degrees Celsius. That's going to be our change. So somebody with one of those fancy dancy calculators that you kids all have nowadays, tell me how much energy that is. And if you need to make your box bigger in here, you can. So take 12,000 times 8.3. What?
99,600.
That's what I got.
99,600. What? What's the unit? Nope.
Calories.
What?
Degrees Celsius.
Calories.
Calories, my bad.
Because these two multiplied together give us calories. The problem is, this is which calorie? How do we get to the big C?
1,000 calories is 1 calorie.
Okay, so we're going to take this times a conversion factor, ladies and gentlemen. Part of this is going to go on top, part of it's going to go on the bottom. Because I want the little c calories to cancel, I'm going to put the 1,000 little c calories on the bottom. I'm going to put 1 big C calorie on top. So when I divide this number by 1,000, ladies and gentlemen, I get 99.6 calories. Big C calories. That is almost 100 food calories. Now think about this. At the store, you can buy snack packs of like Oreos in 100 calories or less. So they will put tiny little Oreos in a bag, and when you eat the whole bag, it's 100 calories or less. I don't know why they do that. I just eat a bunch of Oreos. Okay? So this is literally less than 1/2 of a Snickers bar. We said the Snickers bar was 250 calories. This is about 100. And it could heat a case of water up by 8 degrees Celsius. That's how much energy there is there. Okay? Now, please think about this for a second. How many calories is the average person supposed to take in on a daily basis? Around 2,000. 100 calories heats a case of water by 8 degrees. We're supposed to take in 20 times that on a daily basis for our body. More depending on how physically active you are. Anybody remember a swimmer named Michael Phelps?
Yes.
He was like 15,000 calories a day. A day. And the guy was a stick. Why? Because he burned off that many calories while he swam every day.
Does he have like 30 gold medals?
Yes. I don't know if he still is, but he was at one point the most decorated Olympic athlete ever. I think he still is. Okay? But the point is, he used to take in an incredible amount of calories, and he didn't get fat. Why? Because he would burn them all off in his workouts and things. Depending on how active you are, yes, the average person is supposed to take in about 2,000 calories, but you could take in a lot more depending on how active you are. Or some people take in less. We'll get into talking about that later. It also depends on your age. I hate to tell you this. You guys can take in more calories than I can. Why? Not only that, your metabolism is higher than mine. You're also still developing. Your body is still developing and growing. Mine, the only way I grow is if my belly gets bigger. Okay? So don't worry. Eventually, it'll catch up with you too. Anybody here know what the freshman 15 is? Not lose.
Gain.
Most people, when they go off to college, their first year gain about 15 pounds. Why? Because you change your diet dramatically and your activity level changes as well. Okay? All right. So let's talk, ladies and gentlemen. Let's talk about a sandwich. How much energy would be given off by a double bacon king burger at Burger King if it can warm 5-gallon bottle of water? Now, what's a 5-gallon bottle of water?
That's like a big jug, right?
That is like if you ever seen those water coolers that have the bottle on top of them. That's a 5-gallon bottle of water, just so you know. Okay? 5-gallon bottle of water. Okay? From 20.4 degrees Celsius to 75.4. That's not quite boiling, but that's getting up there. All right, so what are we looking for? What are we trying to find again? We're trying to find energy. Good. Okay? So we're trying to find energy. So in my formula, here's the energy. Okay? Now, we're also have to be given something. We need a mass. Do we have a mass of water here?
5 gallons.
That's not a mass. That's a volume, though. Mass would have to be in what unit? Grams. Where do we have a number in grams? Good. So again, ladies and gentlemen, I'm letting my units help tell me where these things have to go. The only way we measure mass is in grams. Okay? All right. So now I need a change in temperature. Change in temperature, ladies and gentlemen. Change in temperature. What unit would it have to be in? Okay, so where have I got numbers in Celsius?
20.4 and 75.4.
Very good. People always look at these problems and go, man, I can't figure them out. I don't know where to begin. Let your units help you. Let your units help you. So what am I looking for in this problem, ladies and gentlemen? I am looking for energy. And eventually I want to get energy into so many big C calories because we're talking about food, okay? That's what I want to get it into. Okay? So what are we given? Well, I am given a mass, aren't I? What's my mass? Good. I am also given a change in temperature. What's my change in temperature? What is it? 55. Thank you. 55. If you're wondering how we got that, we took these numbers here. 75.4 degrees Celsius minus 20.4 degrees Celsius. Just subtracting these two. And Ethan got 55.0 degrees Celsius. So now we can put everything into this formula right here, ladies and gentlemen. Energy and I'm just going to use E to represent it, is equal to the mass, 18,920 grams, times the change in temp, 55.0 degrees Celsius. Someone do the math for me, please.
Um, 1,000,000.
Just read me the digits.
1040600.
1040600.
Yes.
Good. What unit is this in?
Calorie.
Which ones? Little c calories. This formula gives us little c calories. So I still want to get it into what? Big C calories. That's the same step we ended the last one with. 1 big C calorie over 1,000 little c calories. That means, ladies and gentlemen, that the energy equals 1,040.600 big C calories.
Can we just use the 2 zeros at the end?
You can actually, if we look up here, 3 sig figs here, 3 sig figs here, 5 sig figs here. This answer can only go in 3 sig figs. So in 3 sig figs, we would lose it to that because the 4 is the 3rd sig fig here. Questions? By the way, if you eat one of these sandwiches, just the sandwich, no fries, no Coke, no nothing else, you take in over half your daily calories. So just something to think about. All right. In your Google Classroom, ladies and gentlemen, I put a assignment for you. Let's find it and let's go to it. So it is the, come on. Calculating energy worksheet. Open that up, please, ladies and gentlemen, and it should look like this right here. Okay? Open this up and it should look like this right here. Okay? Now, one other thing we got to be careful of. Is there energy in soda? Yes. Any idea about how much?
I guess.
Sure, take a guess. Give me Mountain Dew. Why am I selecting Mountain Dew? Because I have a teacher save me cans that he drinks, and I get a lot of Mountain Dew cans from him.
4,200.
4,200 calories?
Oh, no.
How many calories would you say there are in a can of soda?
353.
What? Mountain Dew, 170.
Ooh.
170. Oh, by the way, how much sugar do you think is in this one can of soda?
50-some grams.
44 grams.
I was kind of close.
44 grams.
I said
Pepsi, ladies and gentlemen, is only 150 calories.
So why is there
And-
calorie difference?
Because this only has 41 grams of sugar in it,
Oh, okay.
as opposed to 44. Which means there's more energy in this one than there is in this one. Okay? So there is a certain amount of energy in here, correct? But you know what? I'm going to decide that I'm going to maximize my energy intake. I only want to drink 150 calories of energy, but I'm going to drink a 2-liter bottle of Pepsi instead of this can. Would that 2-liter bottle contain 150 grams of,
More
or
than that.
150 calories? Why more?
Because it's bigger.
Thank you. The one thing you need to look at when you look at calories occasionally, ladies and gentlemen, is there's a serving size on here. And sometimes they will fool you. They will tell you that the energy in your bottle of soda is 230 grams and or 230 calories. And you think, that's pretty good because my bottle of soda is a lot bigger than the can. Well, look at how many servings it is. Sometimes it is 2 or 3 servings. How many servings in that one can? Probably 1 because that's a smaller can. Okay.
Serving per can, yes.
And how many calories?
5.
5. Meaning it's mostly what?
Water.
Water. How much sugar?
0.
0. Okay. So that's why it's very low calorie. Okay. So please understand this. There is a second part to this. Okay. So Christian has a bowl of cereal for breakfast, and so does Ethan. They both have the same cereal, but Ethan gets a lot more calories. Why? Because his bowl is one of the big salad bowls that he fills with the box and then throws some milk on it, and Christian uses a smaller bowl. So we got to be careful. There is something else that's involved here, and that is called serving size. Okay? So on this worksheet, I have 2 formulas for you. The first is for energy. Now, by the way, this formula right here puts together what we have just been doing. The mass of water times the change in temp divided by 1,000. Why have we been dividing by 1,000?
So just in place for the little c to big c.
Little c to big C. So this formula is going to get us into energy in big C calories, which is what we want because we're looking at food. However, ladies and gentlemen, when you talk about food, energy, it only comes from the amount of food that you eat. So if you have a bag of chips, a small bag of chips, and you don't eat them all, you don't get all of the energy that is in that bag of chips. You only get the energy from the foods you eat. So the way we are going to do that tomorrow, ladies and gentlemen, is we are going to burn chips. We are going to burn marshmallows. We are going to burn macadamia nuts. But not every one of those is the exact same size. So the way we're going to do it so that we can compare your macadamia nut to Ethan's macadamia nut when they burn is we need to include the energy per gram. The energy per gram. Okay? No, they're going to get burnt. They're not getting toasted. They're getting burnt. Okay? And so you're not going to be eating anything when you're done here, ladies and gentlemen. The chips are going to be burnt. The macadamia nuts are going to be burnt. The marshmallows are going to be burnt. Okay? So, name the 3 variables that are involved in the calorimetry formula and show what letter is used to represent each of these. So what are the 3 variables represented in this formula?
M for mass.
M for mass. Delta T for change in temp. And let's just use E for energy.
Oh, my bad.
No, energy. Calories is the unit, but the variable would be energy.
Okay.
So I hope you're on this and I hope you're putting those in because I just gave you the answer for the first one. E for energy, M for mass, as Zoe said, and delta T for temperature. Now, if you want to know how to put a delta in, ladies and gentlemen, there are a couple of ways you can do it. But when you're in the box, you can go up to the top and you can do insert special character. And you can do one of 2 things. You could type in delta and it will bring up all these triangles for you. Or you can go down here, ladies and gentlemen, and you could try to draw the triangle. And again, it will bring up those triangles for you so that you can have delta. Okay? By the way, here's what I would do. I would highlight the delta T there, Control C, and copy and paste it. Ooh, that didn't work. Didn't like that. Didn't like that.
Can you repeat the first 3? So you said delta T.
M and E for energy.
So M and then E.
Yep. Okay. So, if the amount of food you have goes up, what's going to happen to the change in temperature that it creates? If you have a bigger chip that you are burning, what's going to happen to the change in temperature from that larger chip? It's going to go up. The more food, the more energy you should get. So if that's increasing, how is this going to change?
The temperature is gonna go up.
Increasing. Increasing. If both of these are increasing, what kind of relationship? Direct.
You want us to finish with that again?
I'm trying to give you the answers. I would write them down.
I agree.
So this can has 150 calories of energy in it if you drink the whole can, correct? So this next question, if I only drink half the can, what happens to the amount of energy that I get? It goes down. It goes down. So if I decrease the mass, I decrease the amount of calories I get, correct? Good. What kind of relationship is that?
Yeah.
If they're both decreasing.
Oh, correct.
Both decreasing. Now, lastly, ladies and gentlemen, which one has more calories in it?
The
Mountain Dew. So if I take the energy from both of these and use it to heat up water, this one has more calories, correct? That the calories increase. So what's going to happen to the change in temp if I get more energy out of that one? It's going to get higher or it's going to increase. Very good. It's going to increase, which is what kind of relationship? Direct.
Do we just do this today, Mr. Gray?
What?
Do we just do this today?
Basically, yes. All right. So, this problem. A Snickers bar contains enough energy to raise 172 grams of water from 15 degrees Celsius to 65.0 degrees Celsius. How much energy is released? So this is the formula that we are going to use here, ladies and gentlemen. Now, we don't need to worry about grams burned because we're eating the whole Snickers bar. Okay, we're just trying to figure out how much energy was in it. So this is the formula that we're using here. Now, this number, 172.0 grams, what is that again? Mass, okay? So it goes into the formula where the mass of water goes, which is why I put it in right here for you. Does that make sense?
Yes.
Okay, this 15.0 degrees Celsius to 65 degrees Celsius is the what? Change in temperature. But you need to subtract those two, and when you do, we get 50 degrees Celsius. That's the number that I put right in here. Okay? Then we are going to divide it by 1,000 so that we can get to big C calories. So, ladies and gentlemen, take 172 times 50 divided by 1,000. And by the way, I should put another 0 here. Why? Because these numbers have 3 sig figs. This number has 4. This number should have 3 sig figs. So that is what we come out with. Questions? Okay. All right. So that one was done for you. Now let's go to this one. Okay. All right. And again, this one is done for you. This example is done for you. Okay. Same formula. Now, here's the thing. All that I did in the yellow box was took the formula that was above it, Control-C, copied it, and put it in there. So that is all you have to do. Then, ladies and gentlemen, you're going to go through and you're going to say, all right, 995 grams of water. That's the what? So I take that number and I put it in here where it said mass of water originally, 995 grams. For the change in temp, I put in the two numbers, 62 minus 21. Okay, that gives me a change in temp of 21 degrees. I don't care if you put it in as 62 minus 41 or you just give me the change, the number that you'd get. Either way, I multiply these together, divide by 1,000 and get this. Okay, so again, another example done for you. So let's take a look at number 5, ladies and gentlemen. If a McDonald's hamburger has enough energy to heat 665 grams of water from 4.5 degrees Celsius to 885 degrees Celsius, how much energy does the hamburger contain? So again, I took this, I highlighted it, Control C, and I put it in here. Now, what do we put for mass of water here? I'm going to take out mass of water. What do I put in there? Grams. I'm going to take out change in temp of water. And what do I put there?
885 minus 4.50.
Okay, so I can do 885 degrees Celsius. By the way, sometimes it's easier to just copy and paste than it is to type. I don't know if this is going to work. We're going to try. Okay, I didn't like that degree sign there. Okay, we'll live with it. It's okay. Minus 4.50 degrees Celsius divided by 1,000. So now you need to put this in your calculator. You can put it in all at once, ladies and gentlemen, but to do this subtraction, what do I have to do with it in your calculator? Put it in parentheses. So you hit this, 665 times, parentheses, 885 minus 4.50. Close your parentheses, hit divided by 1,000. Somebody tell me what we get.
585.5325.
So the energy equals what?
585.5325.
What unit?
Little C.
Nope. Big C. Big C. All right, ladies and gentlemen, we'll see you tomorrow. Be ready for your lab.
Alright, I'm ready.
Goodbye, goodbye, goodbye. Go away.
I hope Faith is here because she wants to put a marshmallow.
Well, I can only deal with who's here, not who's not.
She's gonna want to put it.
Well, she will, but she's got to be here to do it.
No, she missed out on a good lab. I'm gonna put marshmallows and make them black. That was an easy speed.
Okay, we'll be doing that tomorrow, Zoe. See ya.
Thank you, sir.
Bye.
I'm making four out of marshmallows.
All right, ladies and gentlemen. Zoe, don't forget your stuff.
I won't.
Good, 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 good. See you tomorrow.
See ya. Mr. Brand.
See ya.